Okay, so, great. So this diagram, it's really awesome. So let's tell you, what is pseudo-isotopy? It's simply, if you start with the manifold, it's simply diffeomorphism manifold cross I to itself takes 0 to 0 like identity, more or less. Identity if there's boundary. But for me, I just hear that definition, just this diffeomorphism. It doesn't really do much. But, to get some type of visceral feel, look at this picture. Really, pseudo-isotopy is a way of assigning sort of a non-standard, typically, product structure on M cross I. So the thing is that, well, to me, just as coming from low dimensions, exists such a thing as actually kind of surprising. But the thing is, what's interesting is this is a way of relating like the identity map on a manifold with possibly another diffeomorphism phi. So if you look at the restriction to the top, since M cross 1 to M cross 1, and if the induced map is phi, then that's a pseudo-isotopy from the identity to phi. So one way is just to look at this directly. Another way is to think in terms of vector fields. So if you have the standard product structure, then if you just integrate it, you get the identity. And if you have another one, integrate that, maybe get something else. Fine. So, right. Okay, so that's the definition. And here's my goals for this talk. One is to give you this sort of just a very quick introduction to the theory of these big results of Cerf, Hatcher, Wagner, Gusse, Quinn. And then talk about sort of like modern applications to four-manifold theory. Now, I use the word application in a question, in quotation, italics, because for me, we're mathematicians trying to prove a theorem, research all different ways to find a solution. Maybe such and such technique works. But to me, there's two types of theorems. Like one theorem you prove, because that's the theorem you want to prove, and okay, somehow you prove it. But then there's sort of other theorems that, okay, while you're racking your head, attempting to prove maybe, theorem 1, you see just like lying on the side, something interesting. So in the pseudo-isotopy theory, I think you'll see that there's both types of phenomena, at least for me. So, right. Okay. So here's like two ancient results, which is simply like, well, if you have two manifolds with the same topological boundary, then you get a new manifold by gluing one to the other. We all know how to do that. However, it's a little exercise. Probably known from the beginning, is that there's some ambiguity, or rather, there's some flexibility. If the gluing maps differ by pseudo-isotopy, then you get the same manifold of the diffeomorphism. So I should say working in the smooth category. But here's another little fact, which is that suppose I glue two end balls together and get the standard end sphere. Then the gluing map is in fact pseudo-isotopic to identity. And this is sort of like a pictorial way of seeing this. Because like here's the glue on the left. And now we're just like gluing these 5 balls together. And now on the right, you can see the balls themselves sitting inside the 5 sphere, which you know is standard. So there's this basic fact of surf and Palais that if you have like a parametrized ball, 2 parametrized balls, end balls, then you can just ambient isotope one to the other. So the point is, like this 5 ball on the bottom, you could just dice it back to the standard 5 ball, one on the other side, other standard 5 ball. And you can see, I mean, if you have 2 standard 5 balls, what's between them is like S4 cross I. But on the other hand, in the process of isotoping these things to be standard, you might see another product structure. And so anyway, this shows how to see this 5 pseudo-isotopic to identity. Okay, so this is a basic fact. First, really big theorem, I think. The subject is Cerf's theorem. And he proved this awesome result that if you had compact simply connected manifold dimension, at least 5, and phi is pseudo-isotopic to identity, and in fact, it's isotopic to identity. In fact, the pseudo-isotopy itself is isotopic to identity. It's just like a really long and hard piece of work. But the idea, you could just summarize it in a manner, which is, remember, pseudo-isotopy corresponds to maybe a standard product structure and a different product structure. Product structure is just a non-singular map of M cross I to 0, 1. In other words, it's just a non-singular Morse function on M cross I. So you have this like standard non-singular Morse function in this other one. And it's a simple fact. The space of projections, M cross I to 0, 1, smooth. It's a contractible space. So you can homotop, these projections, the standard projections, other projections from one to the other. You get a path. And, well, you have just a path of functions, M cross I to 0, 1. And as we probably know, is that if you have a function from M cross I to 0, 1 to a small perturbation, it becomes a Morse function. So in the same manner that if you have this path to a generic perturbation, then you get a 1-parameter family of generalized Morse functions from the standard projection to this new one. So in particular, unfortunately, this thing doesn't seem to work, but if you just pick time t, look at this vertical, then typically you see a Morse function, and those numbers indicate type of critical points. So this simple graph that records sort of the critical point behavior is called the Cerf graphic. So just to summarize, you have a 1-parameter family of generalized Morse functions. So, right, so what is a generalized Morse function? Well, simply, well, a Morse function, has, find critical points, here syntheses. But now we have a family of such, so we need a mechanism for introducing canceling pairs. So you can see, so here on the left, no critical points. Here on the right, single index 1, index 2. So to get from the left to the right, that's what's called a birth. And going from the right to the left, that's a death. So generalized Morse function simply is just Morse functions, but now we have families of one parameter families. So we allow for births and deaths. That's what it is. So you can see this picture. That's sort of these cusps here. Those are the various births. So okay, so that's simply, let me see if it's surf. But now this great theory, Hatcher and Wagner, corrected a bit by Gusa. And so they addressed like the question of, is a pseudo-isotopy isotopic standard for non-simply connected manifolds? And they built this obstruction theory that if you have the pseudo-isotopy and all these obstructions vanish, then in fact the pseudo-isotopy is isotopically standard. Now, this works in high dimensions. So the manifold is at least 6. But to Hatcher and Wagner's credit, they were very careful to note when things have worked in lower dimension. So in particular, they prove that if the manifold is at least dimension 4, and this first Hatcher-Wagner obstruction is equal to 0, then there is a one-parameter family with nested surf graphic, which has some other nice features. Now, this first obstruction lies in this K-theory group, Whitehead 2 of the fundamental group. And these people, circa early 70s, showed that if the fundamental group was free or free abelian, then this K-theory group is equal to 0. So in particular, manifold, this fundamental group, this is E, for example, then this first obstruction is always 0. So here's this picture summarizes 214 pages of Hatcher-Wagner. So you just start with this random graphic, but under the assumption that first obstruction is equal to 0, then in fact you get this nested I graph. So let me point this out. So how does the Morse function change as you go from the left to the right? So you can see here in this picture, let's say there's 3 births. Now, if we were in dimension 4, so we're talking about m cross I, m is dimension 4, then the effect at the middle level, like right here, there you would see m connected to some 3 copies of S2 cross S2. So this picture over here is sort of a 3-dimensional slice of that. So by which I mean, you look at the critical points of index 2 and you look at the ascending sphere, then those are two spheres in this dimension. And the descending spheres are also two spheres. So just after the cusps, what you see is S2 is the manifold some S2 cross S2. Three of them in this case, where you see three sets of ascending and descending spheres, just totally standard looking. To me, my mind, green is always ascending spheres of 2 handles, red or descending spheres of 3 handles. Okay, now here's the interesting thing, is that here, now as you go along, shift from left to right, then what happens is gradient-like vector fields changing. And you know we change the gradient-like vector field. Possibly create new intersections between ascending and descending spheres. So as you go from left to right, you see maybe some number of finger moves where it create pairs of intersections. Some number of Whitney moves, maybe 2 finger moves, Whitney moves, 4 finger moves, Whitney moves. But in the end, you literally here, and everything's back to geometric delta ij. So that's sort of an idea of what happens in this Hatcher-Wagoner situation. So, right, okay. So before I come back to this graphic, but before I do, let me mention a couple of theorems on the existence, non-existence of pseudo-isotopies. Well, first there's the theorem independent of Sato and Lashoff-Shanison, 68, is that if you have a diffeomorphism, S1 cross S3, which are homotopic to the identity, then it's pseudo-isotopic to the identity. And the thing that, actually it's a very short argument, but what powers that is Shannison's thesis, which would show that there's unique differentiable structure in S1 cross S3. So the argument I gave for unique differentiable structure on 5-sphere implies the gluing map is pseudo-isotopic to identity. In the same manner here, you can, but then there's Craig's theorem that you have closely connected manifolds, diffeomorphism, homotopic to identity. It's also pseudo-isotopic to identity. Here, he's somehow using surgery theory. On the other hand, unlike higher dimensions, Danny Ruperman, using gauge theory, showed that there's diffeomorphism of a closed, simply connected manifold, homotopic to identity, that's not isotopic to identity, but in fact, it's topologically isotopic to identity. So, finally, I want to mention Kranich-Cooper's very recent, where the fundamental group is free and the manifold's closed and orientable, then homotopic to identity implies pseudo-isotopic to identity. And he also showed there's diffeomorphisms, not pseudo-isotopic to identity. So, right. So there's some things to think about. But let's get back to taking Hatcher-Wagoner to another level. And right now, right here is an incredibly simple but powerful observation of Frank Quinn. And Frank Quinn's observation is that if you have one of these nested graphics, then all the data, in some sense, is concentrated in one little spot, the middle level. So if the ambient manifold is like 4 dimensions, you're looking at M cross I, and the one parameter family, 6 dimensions. But this one 4-dimensional manifold, together with some other bits of data, determines all the information. And the bits of data is simply, for this manifold, you're looking at the ascending spheres, 2 handles, descending spheres, 3 handles, lots of intersections. But the data is simply 2 sets of complete Whitney disks. So if I have a collection of Whitney disks that sort of cancel the excess intersections, then using them, I could start here, do all this cancellation. Now I'm delta ij geometrically. Then I can do all the f's. So I go this way. And in the other direction, if I have a second system, I can use the other second system, Whitney disks, to go this way, delta ij intersection. And then so do the depths here. So if I have these 2 sets of Whitney disks, I can complete this picture. Conversely, if I have just a Hatcher-Wagoner picture, just using sort of the usual, exchange of order of critical points under such and such circumstance, then you can arrange that all the finger moves occur before any of the Whitney moves. So once you do that, then you're in Quinn situation. So this sort of summarizes just the introduction to pseudo-isotopy theory. So now, whoops. So here's sort of a typical picture of the middle level, where we're looking at like a 3-dimensional slice, and there's green spheres, the ascending sphere, 2 handle, and we have a bunch of intersections with the descending spheres of 3 handles. So I've sort of shaded them in, these what we call finger disks. And you could see that if you use them, then you could just sort of undo the picture and get something sort of just completely, just geometric delta ij. But if you have another system of Whitney disks, then again, as I just mentioned, you can do them and also get something delta ij. And then you can sort of fill in the picture this way. So some years ago now, like I was staring at this picture. I said to myself, look, you're supposed to have like these standard fingers. And we do the finger moves. And then we're back to the exact standard, the green, red, ascending, descending spheres. On the other hand, suppose we just do the Whitney moves. Well, fine. Now we're in a situation where we're geometrically delta ij. But the question is this. You have now sort of a delta ij system of red spheres and green spheres. And I know what the standard picture is. The question is, can I sort of isotope this delta ij, like picture of these funny red spheres, to the standard one by an isotopy, keeping everything delta ij. So, right. So the answer is, well, okay, well, here's the question again. So, right. Okay, so can you do this? And the answer is yes. That's what the light bulb theorem does. So, okay, you probably heard about the light bulb theorem. Gave a lecture here last year, FSA thing, and But the thing is, I didn't go looking to prove the light bulb theorem. Rather, I just really wanted to understand pseudo-isotopy. And he asked this sort of like really naive question. And it turned out the solution was kind of interesting. And in fact, if you just do any system Whitney disks, you can bring them back to the original set without creating a extra intersection. So let me just simply quickly tell you this. And I mean, I'm just stating for just a single pair, but light bulb theorem says that if you have two spheres with a common dual sphere, by dual sphere, I mean it intersects each once and has a trivial normal bundle, that if they're homotopic, they're ambiently isotopic. And without creating, you could do this ambient isotopy without creating extra intersections between the spheres and the dual sphere. So actually, what I said is not quite true, because the way I proved it did two torsion in the fundamental group. Hannah Schwartz, in our thesis, showed that in fact it's a necessary condition. But Rob Schneider and Peter Teichner showed that in fact they discovered that the Friedman-Quinn invariant is the exact instruction for homotopy versus isotopy when you have two torsion. But the funny thing here is we know the systems of spheres are isotopic. I mean, they came about by, I mean, just the isotope just crashes through the green spheres. So, but the fact that they're isotopic means that the Friedman-Quinn invariant vanishes. So in fact, you can, even when there's two torsion, isotopy back. Okay, so that's sort of the first thing where pseudo-isotopy sort of at least inspired a theorem. So let me show you a next one. Oh, before I do that, let me just two other related theorems. Well, one is that if you have a diffeomorphism of S4 homotopy identity, then somehow it comes from a loop of red spheres. And Crouch and Cooper's generalized this to simply connected. And more generally, you could do that if diffeomorphism pseudo-isotopic by pseudo-isotopy with trivial first Hatcher-Wagoner obstruction. So right. So the point was that if you start here, you did the finger moves, then you did the Whitney moves, then you can do more isotopy. Get back to where you started. Okay, so that's like the first theorem, and now let's. So here's sort of a second theorem, which somehow I learned about from just staring at pseudo-isotopy. So if I have a diffeomorphism, it's a homotopic to identity. Suppose I could do the following. I could do some isotopy so that in some disjoint union of four balls, the diffeomorphism is the identity. Now in those four balls, I connected some S2 cross S2. And now I have this new manifold, but extended diffeomorphism to be the identity on these S2 cross S2 factors. Suppose I can do this. And the resulting diffeomorphism is now isotopic to identity. Then we say that this diffeomorphism is stably isotopic to identity. So the theorem is there's a necessary and sufficient condition for diffeomorphism to be stably isotopic to identity. And the condition is it's stable isotopic to identity. If it's pseudo-isotopic to identity, find pseudo-isotopy with trivial Hatcher-Wagoner first obstruction. So here's sort of like the picture. Now, if you look at the picture on the left, there's the Hatcher-Wagoner picture. That dot corresponds to, the Quinn middle level. Now, I spent a long time staring at this diagram. And, just with this little dot in the middle, sort of just get hypnotized. But eventually, you just let your eyes blur. And if you say to yourself, well, instead of thinking about dot, maybe we could understand like this, somehow this whole inside region. And so let me just say this, which is using a little bit of, more than a little bit of technique from DavidGabai in this theorem I just mentioned. You can arrange this picture so that we go from this spot to this spot. All these one parameter family of Morse functions. It's the same exact Morse function. What's different is that as you go from left to right, the gradient like vector field changes. So the thing is that if you sort of like just clean up, normalize this picture, then every point in here is canonically manifold connected some number of S2 cross S2s. So now we have two gradient-like vector fields. We have sort of like the trivial one coming from the one all the way on the left, but we could just use the trivial one left to right. But we also have the other gradient-like vector field. So the beauty of having two gradient-like vector fields is that the first one somehow gives you a set of coordinates on this box. So every little vertical line is connected some S2 cross D2s times the interval. So when we use the second gradient-like vector field, somehow we see a path there. Well, okay, let me just take my word for it that if you can arrange this picture so that using two applications of the light bulb theorem is that you start sort of standard green and red spheres here, and then when you get to here, you're back exactly to the standard ones. So the upshot is that you sort of like just organize the data inside, and literally inside sort of this eye of the one parameter family diagram, you literally see stable isotopy right here. So, well, okay, some technical things is why is that this stable isotopy is the right thing? But anyway, somehow use this Jensen-A uniqueness of death and some other things. So, okay, so that's somehow using pseudo-isotopy theory to solve this problem, necessary and sufficient condition of diffeomorphism being stably isotopically trivial. So, and I should say again, this is not something I sort of went looking for. Well, that's an interesting question. So let's find a solution. Rather, I said, okay, well, what I really care about is pseudo-isotopy, for such and such reasons I'll mention later. So like I have this rug and I'm just shaking it out and looking at it from all different directions. And sitting there is this little piece of structure about stable isotopy. Okay, so next thing, I should mention this, is that something stable isotopic identity, pseudo-isotopic identity with trivial heterowagon invariant. I mean, maybe it's always stable isotopic identity, right? I mean, in the spirit of 4-manifolds, if you have something, you stabilize it enough, it should be the standard thing. So maybe I just have like a fancy statement that's sort of vacuous. But thankfully, this recent theorem of Cranach and Cooper's shows there's closed orientable 4-manifold and a diffeomorphism homotopic to identity. It's not pseudo-isotopic to identity. So in particular, here's the diffeomorphism homotopic to identity, but it's not stable isotopic to identity by this theorem. And Mark Powell has an example of diffeomorphism pseudo-isotopic to identity with non-vanishing heterowagon invariant. But it's possible that in this case, there's another pseudo-isotopy that maybe that one is trivial. But in any case, right. So excuse me. It's nasty cold. Right. Okay. So here's the next item. So the previous theorem was about stabilization of diffeomorphism. Here we have a theorem, basically Quinn from 1986, that stabilization of the pseudoisotopy itself. And his theorem is that if you have diffeomorphism of a simply connected manifold and you have a pseudoisotopy of it, then in fact pseudoisotopy is stably isotopic to identity. Well, I sort of say all the words for what it means, but you can imagine now you have this M cross I and just a little point cross I with a diffeomorphism identity, and put on connect some cross I. So I mean, it's a beautiful theorem, but it suffers from the problem that a crucial lemma is the proof is simply problematic. And in fact, this crucial lemma, which is known as disk replacement criterion, it's probably false. I'd conjecture it's false. However, the good news is that we have this 5-person paper, myself, DavidGabai, Daniel Hartman, Slava Krushko, Mark Powell, that we can somehow fix Quinn's proof. So I mean, Quinn's proof is this brilliant thing, and unfortunately, as a lemma, it doesn't work. But using some of Quinn's ideas and some new ones, we can fix it. And one of the new ones, well, maybe the new one, which is sort of a new technique, is this technique of factorization, which more or less is a composition rule for Finger-Whitney systems. Remember, Frank Quinn's middle level, the data is determined by 2 sets of Whitney disks. To have 2 sets of Whitney disks is enough to get a diffeomorphism. So this factorization rule tells you that, well, if you have the diffeomorphism coming from like W2 and W3, and you compose it with diffeomorphism coming from W1, W2, then that's the same as diffeomorphism coming from W1 and W3. Anyway, that's sort of the new ingredient we have. So, right. Okay, but let me just mention this, which the reason why Quinn was interested in that is because he's very interested in smoothing theory. And this sort of stable pseudo-isotopy theorem enables, assuming that Quinn was able to prove this pi for this group top 4 modulo O4 is equal to 0, which is a fundamental theorem in smooth 4-manifold smoothing theory. Okay, so okay, right. But before giving this survey, this talk, I should mention this foundational basic theorem that Perron-Quinn proved in 1986 using pseudo-isotopy theory. And the theorem is, if you have a diffeomorphism homotopically trivial on a manifold that's simply connected, then if it's homotopic identity, it's topologically isotopy identity. So this is the theorem Ruberman used to say that, well, here's a diffeomorphism that's topologically isotopic to identity, but using gauge theory, it wasn't isotopic to identity. Now, both those theorems use pseudo-isotopy theory, but also, Mike Friedman's spectacular disk embedding theorem. And I should also say that Quinn's proof, well, needs to be fixed up. But the great outcome of that theorem, together with Friedman's work, is that if you have a, say, closed simply connected manifold, then the mapping, topological mapping class group is isomorphic to the group of automorphisms of H2 preserve the intersection form. So, right. Okay, so, so now I'll tell you the next thing. It's the idea of carving surgery presentation. So, this diagram is supposed to give a schematic for it, but maybe just go straight to the definition. So you can imagine, like, here we are in the 3-4 sphere, and here's the standard 3 sphere, and the standard 3 sphere bounds southern 4 ball and the northern 4 ball. So the point of this carving surgery presentation is starting with the standard thing, giving a way of sort of describing any smooth 3-sphere and 4 space. Now, what I'm about to describe for you is a process that proves that that enables the construction of lots of different manifolds. But I sort of went through this quickly. But the theorem is that if you have a smooth 3-sphere, then there's a carving surgery presentation that sort of describes it. And furthermore, in a way that it's sort of obviously 3-sphere. I mean, the presentation might be a bit complicated, but at least you know it's what you've got 3-sphere. So here's the process. You start with the standard 3-sphere, bounding, say, the southern 4 ball. Now you have a bunch of, say, a links in that 3-sphere, and now you attach 2 handles along that link. But the rule is those 2 handles have to be embedded in the northern bowl. Everything in this process, but it all happens in the 4-sphere. So to the southern bowl, we add 2 handles. But from the northern bowl, that has the effect of carving out 2 handles. Now, concurrently, from the southern bowl, carve out a bunch of 2 handles, and which is from the northern part, adding 2 handles. So that's the first step. Okay, but now you iterate this finally many times. So, by which I mean, in the second step, again, you start out with a link. It's now, again, it's living in the 3-sphere, but it's living in the bound. So we modified the southern wall. It's new southern wall. I guess I call it like X1S. And there's some links sitting in the boundary, which is still a standard sphere. But now, again, you attach a bunch of 2 handles. But here, the 2 handles have to live in the modified northern part. So, on one hand, it's more restrictive, but on the other hand, it's more flexible. It's more flexible because, remember, we carved out 2 handles from the south. So if I'm adding a 2 handle to the south, in the second step, it's allowed to go through the space that was sort of created in the first step. So anyway, that's anything just defined this way is a carving surgery presentation. If it has certain extra features, I call it a Finger-Whitney carving surgery presentation. So here's like a particular simple one where if you look over there, there's a slice link, so I'm attaching a 2 handle there, but now here's like a little linking circle, and now I'm like removing a potentially very complicated 2 disc, which is going through that 0 handle, and so that's our new manifold. Anyway, it turns out it's a fact that this is actually a 4-bowl. So, but before I let me just take a slight detour, which, just sort of suggests the following problem, which is spatial-elasticity more general. Like, you have the trefoil, and now you're adding a 2 handle to the southern bowl along the trefoil with 0 frames. Now here we're out of the category of S4 because trefoil doesn't slice. But suppose we just do it anyway. The southern bowl with this 2 handle, and now we're carving out some disc whose boundary is a standard linking circle, and this disc is required to sort of go through the core of this 2 handle even number of times. Anyway, it's a nice little exercise to show this is what I call Poincare bowl. It's a homotopy 4-bowl, boundary 3-sphere. And so I think it's a fantastic question. If you have homotopy 4 bowls built this way, are they standard? When I showed this to Rob Kirby, he immediately called this a way of constructing bushel basket of homotopy 4 bowls. So anyway, that's an aside. So let's get back to this thing. So the theorem is that any smooth 3-sphere in 4 space has such a presentation with special properties. So you're probably wondering in this talk about pseudo-isotopy, like what does this have to do with pseudo-isotopy? So the answer is a bit complicated, but let me try to give you a hint, which is, so here's, here's the explanation, and I'll just do it ever so briefly, which is, Barry Mazur in 1958 showed that if you have a smooth 3-sphere and 4-space, that's a topological 4-ball. So, a consequence, a very simple consequence of his work, is that if you have any 3-sphere and 4-space, it can be built by starting with a diffeomorphism of S1 cross S3, and just consider a point cross S3. Look at the image under that diffeomorphism of point cross S3. Now you get this complicated 3-sphere S1 cross S3. Lift it up to universal cover, R cross S3. Stick that in the 4-sphere. So that's that's a way of producing all smooth 3 spheres. Okay, but the point of this, what's makes it interesting to me, here's the question about this Schoenflies question. It reduces to a question about diff S1 cross S3. And as I mentioned earlier, Lashoff and Shanison showed that any diff of S1 cross S3 homotopy identity, pseudo-isotopic identity. Pi 1 of S1 cross S3 is Z. So the first Hatcher-Wagner invariance equal to 0. So that fact, plus the Hatcher-Wagner theory says that the pseudo-isotopy has a nested I. Quinn tells us that the diffeomorphism is determined by these Finger-Whitney data. Now notice that if you have like the middle level, okay, you have like the finger disks. Okay, that's one system. But now you have the Whitney disks. The Whitney disks could just cancel, different set of points than the finger disks do. But even if they do, cancel the same points. I mean, the Whitney arcs. I mean, the boundary of the Whitney disks of one system and the other, they could be completely different. Okay, but suppose they're the same. Then, well, there could be twisting of their germs of the boundary one relative to the other. Okay, but suppose they're untwisted. And anyway, there's several other ways you can improve this. So step 5 is try to make the Whitney disks and the finger disks look as much as possible. Okay, so here's where it gets interesting, which is I want to be able to somehow use all this theory to get a description of a 3-sphere and 4-space. So the idea is very simple. Is here we have this non-singular Morse function. Here we have like the standard 3-sphere. What I have to do is just flow it down and get down to here, and now we'll get sort of this new the Schoenflies 3-sphere. So, well, of course, that's easier said than done. Who knows what the vector field is? So, but on the other hand, we have some understanding of this one-parameter family. So we simply just start every spot here, look at the standard 3-sphere, and just flow it all the way down to the bottom. And now just compare those 3 spheres as down at this level and see what happens. Now, of course, probably some of you are just like shaking your head. They've lost it, because the fact is that if you have some object up here, you have these critical points, index 2, index 3, and it could be that some gradient line from one of these critical points sort of crash into your sphere. So there's no way that you can just flow it all the way to the bottom. But what if you say, well, I don't care, you just do it anyway to see what you get? So anyway, to make the long story short, if you do that, what comes up here is a 3-sphere, some description, And it turns out that it has this carving surgery description. So anyway, that's sort of extremely brief, but that's sort of the connection of where this carving surgery business comes from with respect to pseudo-isotopy theory. You know, I need to mention one thing that doesn't have anything to do with pseudo-isotopy, but I have to mention anyway, which is, before I do that, here's a reference. So if you want to learn more, look at this paper, 3 spheres in 4 space, pseudo-isotopies of S1 cross S3. And there, you can find proof of this stabilization term. Learn about factorization, the proof of the carving surgery theorem. So here's this one more thing I need to mention, which is sort of implicit from Barry Mazur's, just great work, but also connecting spheres with Diff. You know, implicit is, well, is Diff of S cross S3 modulo Diff before? Maybe there's just only one element. So there's a bonding out by Diff before. Because Diffeomorphisms of S1 cross S3 and off in some corner, I modify it. Well, okay, that's really interesting, but there's no sort of implications on the Schoenflies problem. So you must mod out by those. But in fact, Ryan Budney and myself and Tadayuki Watanabe, 2021, showed like that if you look at the group of Diff S1 cross S3, hematonic identity modulo Diff B4. In fact, that's infinitely generated. However, all those diffeomorphisms, if you fix one of them, then when you pass the funny sheet cover, it suddenly becomes isotopically standard. So yes, we have interesting diffeomorphisms, but from the point of the Schoenflies problem, what you need is an interesting diffeomorphism that stays interesting when you lift to arbitrary finite covers. Another reformulation of this is the existence of knotted 3 spheres. They're non-separating in S1 cross S3. So here's a picture of such a thing that I discovered. Here's a knotted 3 sphere. However, as I just said, it becomes isotopically standard if you lift to a sufficiently high finite cover. So it's true for all of our constructions, and also Watanabe, because he comes at it differently, something called graft surgery, but all his diffeomorphisms turn out to be sort of compositions of barbell diffeomorphisms, which is what Ryan and I use. So anyway, thank you for your attention.
Questions or comments?
Is there a bound on the number of these operations? So starting from a 3-sphere in S4, as carving and handles.
Yeah.
Probably not.
Actually, I think, sorry, I forget the number, but I think you do it in like Maybe 4, but like certainly 6 or 8 iterations. I think you can get anyone that way.
Or more questions? If there's no question, let's thank the speaker again.